Okay, for the last few years, the big tech giants have been locked in this crazy arms race. The whole idea has been that to get smarter AI, you just have to build bigger and bigger models. But today, we're going to look at a fascinating new model that asks a totally different question. It's called the Hierarchical Reasoning Model, and we're going to figure out if its groundbreaking approach is the real deal, or maybe just a little bit of hype. All right, let's get into it. You know, for the longest time, the thinking in AI has been pretty simple. Scale is king. Just get more data, add more parameters, and throw more computing power at it. And you see companies pouring billions into building these gigantic models, all based on that same transformer architecture. The assumption has just been, well, this is the only way forward.
But what if that whole assumption is wrong? Well, that's where this story gets really interesting. A small research lab out of Singapore called Sapient Intelligence is basically challenging this entire obsession with scale. They're suggesting that maybe, just maybe, a smarter architecture is way more important than sheer size.
And when I say small, I really mean it. Their new model, the Hierarchical Reasoning Model, or HRM for short, has just 27 million parameters. Seriously, that's not a typo. 27 million. I mean, the difference in scale here is just staggering. We're talking about a model that is literally thousands of times smaller than the giants from OpenAI or Anthropic. It's a true David versus Goliath situation. So, how on earth could a model this tiny even begin to compete? Well, it all comes down to the fundamental problem it was built to solve.
So this entire AI revolution we're living through, it's all built on transformers. They are incredibly powerful for sure, but they have a massive Achilles heel. There are certain kinds of problems they just completely get stuck on, and it doesn't matter how big you make them.
Let's just use a super simple example, Sudoku. Think about how you solve a Sudoku puzzle. You can't just stare at the whole grid and know the answer. You have to try something, right? You put a number in a box, you see if it works with the rules, and if it leads you to a dead end, you have to go back. You backtrack and try a different number. It's all step by step. And this whole process is what we call sequential. Every single step completely depends on the one that came right before it. You can't possibly figure out what to do on step 4 until you've already done steps 1, 2, and 3. And boom! This is exactly where the problem is. Transformers are designed for what's called parallel processing. They look at all the information at once. That's fantastic for understanding language, but it's terrible for problems that need a long, careful, step-by-step chain of logic, like backtracking. So here's the absolute crucial point. A transformer has a fixed number of layers, right? That means it has a limited computational depth. If a reasoning problem needs more sequential steps than the model has layers, it physically cannot solve it. It just hits a wall. And it's this exact limitation that prevents a standard transformer from being a truly universal problem solver.
Okay, so how does HRM actually get around this fundamental roadblock? Well, the magic is all in its architecture. It's built from the ground up to be a totally different kind of thinking machine.
What the creators of HRM did was they essentially gave the transformer a scratch pad, but a scratch pad that exists inside the model itself. So they started with a basic transformer, but then they added this inner loop. It's called latent recurrence. And what it does is it lets the model think about something, then feed its own output back to itself to think for another step, and then another, all without needing more layers. Then they split this whole thing into a hierarchy.
And this is where it gets really cool. They were actually inspired by how a mouse's brain learns. So they created two models that work together. You've got a low-level, or L model, that works super fast, grinding through the details. And then you have a high-level, or H model, that works slower, taking in the results from that L model to see the bigger picture. It's like a multi-speed thinking process all in one system.
But the real secret sauce, the thing that makes this whole thing sing, is the outer loop. Because on top of all that inner thinking, the entire model can run through a problem, come up with a partial answer, and then feed that whole result back into itself to try again and refine it. This lets it take multiple passes at a really tough problem, getting closer and closer to the right solution with every single cycle. So, okay, we have this very clever, multi-loop, brain-inspired machine. It sounds great on paper, but the billion-dollar question is, does any of this actually work in practice? Let's circle back to Sudoku. Remember how we said standard transformers get stuck? They totally plateau at around 60% accuracy, and it doesn't matter how much bigger you make them. Well, with its ability to loop and backtrack inside its own head, HRM achieves near-perfect accuracy. It just completely blows past that fundamental limitation. But the thing that really made everyone's head spin was its performance on the ARC AGI leaderboard. Now, this is a notoriously difficult benchmark for abstract reasoning, and yet, there it is, this tiny 27 million parameter model sitting right between giants like OpenAI's GPT-4o and Anthropic's Claude 3. Insane.
Of course, a result like this seems, well, impossible, right? A model that's thousands of times smaller is performing at the same level as the world's most advanced AIs. It just didn't add up, and it led a lot of people, including the guy who created the benchmark, to cry foul.
And yep, here's the catch. To get these incredible results, the researchers basically took the test problems, created thousands of slightly different versions of them, and added all of that to the training data. On top of that, they gave the model a special hint, basically a cheat sheet, telling it what kind of puzzle it was supposed to be solving. And while this might not technically break the rules, critics jumped up to say it completely violates the spirit of the test.
So what this really all means is that the test just wasn't fair. The whole point of the ARC benchmark is to see how well an AI can reason about a problem it has never seen before. But in this case, HRM was essentially familiarized with the problems beforehand, so it just wasn't an apples-to-apples comparison. Not at all. So after all the hype, all the excitement, and all the controversy, what should we really take away from this hierarchical reasoning model?
First things first, it is so important to remember that HRM is not a competitor to something like ChatGPT. It's a highly specialized model. It's built for one type of task. You can't ask it to write you an email or a poem. So comparing it directly to a general-purpose model like GPT-4 is just, well, it's totally unfair. Now, a much fairer fight is to put it up against a standard transformer of the exact same size, trained in the exact same way. And when you do that, HARM still comes out on top. But look, the gap is much smaller now, only about 5 percentage points, so the architecture does give it a real, measurable advantage. It's just not a world-breaking one.
So, what's the verdict? Look, HRM is not the GPT killer that some of the headlines screamed about. The hype was definitely overblown. But the substance? The substance is absolutely real. The model's clever use of these internal loops of recurrence represents a genuinely valuable and new direction for AI research. It proves that architecture can matter just as much, if not more, than just raw scale.
You know, in the end, a lot of researchers believe that the way we make models reason today, by having them write out their steps in what's called chain of thought, is really just a temporary hack. The real future might actually lie in building models like HRM, models that can perform that complex reasoning internally. So, while this specific model might not be the one to change the world, the spirit of this paper and its focus on smarter, more recursive architectures, that will almost certainly live on.